A very warm welcome, guys. Let me remind you the topic where we were. Basically, I told you that sine function from the collection of all reals to the collection of all reals is neither on1 nor onto. But any function can be made onto if the codomain is replaced by the range, and range in this case, in case of the sine function, is nothing but the closed interval -1 to 1. And therefore, when I took function f, which is the sine function from the collection of all reals to the range -1, 1, the function sine came out to be onto because we treated the codomain and made the codomain consist of those members which satisfy the condition of ontoness. But we observed that once ontoness was established, we came and saw the domain, and the domain, which is the collection of all reals, was creating the problem in establishing the oneness of the sine function. Now, by replacing the codomain with the range, ontoness problem was treated. The only thing left was to treat the domain, which is the collection of all reals, in such a manner that the oneness problem is also treated without disturbing the already established ontoness of the function. That means we wanted and wished to restrict this entire domain to a very small subinterval in such a manner such that the graph of sine corresponding to that subinterval does not possess any turns. That means satisfies the horizontal line test, which means satisfies the condition of being 1, 1 without disturbing the already established ontoness of the function. So that is what was my task, and I told you how I restricted my entire domain, which is the collection of all reals, to just the subinterval, which is -pi by 2, pi by 2. Corresponding to this subinterval, the graph which I got was this portion, which is definitely not consisting of any turns, and not just this. In fact, it is covering every value from -1 to 1, thereby not disturbing the ontoness of the function. And thus we said, by replacing the codomain with the range, we treated the ontoness. By replacing the domain with that subinterval corresponding to which there is no turn in the graph, we obtained the oneness of the graph, and therefore f from -pi by 2, pi by 2 to -1, 1. Mind it, only when the domain is this and the codomain is this is my function sine x bijective. But we all know that bijective is another name for being invertible. And therefore, f from -pi by 2, pi by 2 to -1, 1 such that fx equals sine x is invertible. That means when I have the sine function accepting inputs from this interval, that means when I take the machine f to be equal to sine x, then only corresponding to inputs belonging to -pi by 2, pi by 2, and the outputs which this function will be producing inside -1, 1. That means only when the inputs are coming from this interval and outputs are going to this interval can I guarantee that there exists for sure another machine which will be accepting as inputs the outputs produced by sine. That means this y belonging to minus 1, 1 will go as input inside this machine, and the inputs of sine will become outputs of this machine, and that is this. What I am trying to stress on is that it is possible, definitely possible to reverse the working of the machine sine, but only and only when the inputs are coming from minus pi by 2 and the finished products are going in minus 1, 1. Because it is only corresponding to these finished products which are members coming from minus 1, 1, it is only corresponding to these finished products that this reverse machine is able to obtain those raw materials which produced these finished products. Not corresponding to any other product inside the codomain is it possible to get a point in the domain, because the function only from minus 1, 1 kept as the codomain was on 2. And therefore, it is only and only when the inputs are coming from this interval and outputs going in this interval is it possible to reverse the working of this machine and make these finished products enter as input in this reverse machine and get the corresponding outputs as inputs which were used by this machine. And this reverse machine, I am guaranteeing, is existing with this domain, this codomain, this its domain, this its codomain. This is existing for sure because my function sine from this interval to this interval is invertible, and thus there exists the reverse machine known as sine inverse x. Thus, it is possible to reverse the working of the machine sine, but only and only corresponding to these inputs and these outputs. And thus I can say, because my function f from this very good domain because of which my function is 1, 1 and this very good codomain because of which my function is on 2 is a bijective function, and thus because f from minus pi by 2 to minus 1, 1 is bijective, therefore there exists f inverse from minus 1, 1 to minus pi by 2. That is why, because the output set of f, which is this, now becomes the input set of f inverse, and the output set of f inverse is nothing but the input set of f, and that is why the domain of f inverse is nothing but the codomain of f, and the codomain of f inverse is nothing but the domain of f. So there exists for sure, there is a guarantee that there exists f inverse from here to here such that this f inverse, when any finished product is inserted in f inverse, produces that raw material which when was inserted in the machine f produced y as the finished product. That means f inverse y is x if and only if fx equals y, where x acting here as the element of the domain of f or the element of the codomain of f inverse is the same, x belonging to minus pi by 2, and y belonging to codomain of f or domain of f inverse, which is minus 1, 1. This is a very important note to be understood. This f inverse corresponding to f actually is equal to what? Well, because f is nothing but the sine function, f inverse is nothing but the sine inverse function. And thus, sine inverse, I can just write it as a small note. Sine inverse function from where to where? Well, from minus 1, 1 to minus pi by 2, pi by 2. This function is defined as sine inverse y is equal to x if and only if sine x is equal to y. It is only corresponding to y belonging to minus 1, 1 and x belonging to minus pi by 2 is this relation valid, because we are just confirmed that sine from minus pi by 2 to minus 1, 1 is invertible, and that is why sine inverse can only and only take values when this x belongs to minus 1, 1. That means the inputs which are valid inputs for sine inverse are just the members of minus 1 to 1. That is only when is this rule valid. If I talk about the graphical study of sine and sine inverse functions, how do you think will I proceed? Well, if you remember, only corresponding to a specific subinterval was my function sine invertible, and which was minus pi by 2, pi by 2. It was corresponding to this subinterval that my function sine was invertible, because corresponding to this portion, the graph which followed was this. This was the graph of the sine function corresponding to the subinterval minus pi by 2 attaining the height 1 and minus 1 from both the ends. And this is what, because passes the horizontal line test, also covers every member from minus 1 to 1, is the graph of a bijective function or an invertible function. The moment you have a graph of an invertible function, from this graph of the invertible function, you can actually form the graph of inverse function. Because this is the graph of fx equals sine x only from minus pi by 2 to minus 1, 1, that means this is the graph of an invertible function, because sine from minus pi by 2 to minus 1, 1 is an invertible function because it is bijective from this domain to this codomain, and therefore the moment you have this, which is the graph of the invertible sine function, from this very graph of the invertible sine function, I can very well form the graph of the inverse of sine function, which is the sine inverse function. How am I going to do that? Well, for that we need a generalized way of obtaining the graph of f inverse with the help of graph of f. How is that done? Let's keep starting our study upon that. Well, let f be an invertible function. What does this imply? This implies f inverse exists. For sure, If f is invertible, f inverse is existing as a function. And let the following be the graph of f. Suppose, for example, I take this to be the graph of f. Just for a certain example, I am taking, let this to be the graph of f. Then, because I am sure that this is the graph of an invertible function, because I am given f is an invertible function, if you can just look at it as the graph of an invertible function, then there is a guarantee that you can, from this graph of an invertible function f, can obtain the graph of its inverse function. And thus, graph of f inverse can be obtained by what? Well, by taking the mirror image of the graph of f along the line y equals x. What does that mean? It means the moment you have the graph of this invertible function, draw the line y equals x. The moment you draw the line, which is nothing but y equals x, take the mirror image of the graph of f, making this line y equals x act as the mirror. So if you take the mirror image of this portion of the graph of f against the line y equals x comes out to be like this. And if you take the mirror image of this portion against the line y equals x, it comes out to be like this. And the mirror image of this left out portion goes like this, and thereby giving you the graph of f inverse from the graph of f. By using this technique, it comes out to be what? Just observe the mirror image and you get, that is, graph of f inverse is given as follows, which is, just observe the trace which actually is representing the mirror image of the graph of f, and that is nothing but something like this. And therefore, just because you were aware about the graph of f, you are always aware about the graph of f inverse. Now you might be thinking, how did I know that from the graph of f, if I take the mirror image of the graph of f against the line y equals x, I am going to get the graph of f inverse? Why am I so sure about it? Well, I am so sure about it because if x comma y belongs to f, for example, because f can be as seen as a relation also, a specific type of relation also is a function, and so if x comma y belongs to f, this means the first component acts as the input and the second component acts as the output. So this means when f is acting on the input x, it is producing the output y. And if I am sure that the f inverse exists, then if I know that corresponding to the input x, f is producing y as the output, this would imply f inverse, when will take this y as its input, will produce x as that output. And this would mean y comma x belongs to f inverse. This means whenever a point belongs to an invertible function, just swap the positions of both the components, that ordered pair belongs to the inverse of that function. And what does that mean? Suppose for example, I take 2, 3 belongs to f and f is invertible for example. Then this will imply 3, 2 belongs to f inverse. So what is the relation between this point of f and this point of f inverse? The relation is, if you start plotting, where is this point 2, 3 situated? Well, this is 1, this is 2, this is 1, this is 2, this is 3. So this happens to be your point 2, 3. And where is the point 3, 2 situated? Well, just take this 3, this 2 and you get, this is your point 3, 2. Now 2, 3 is a point belonging to f and 3, 2 is a point belonging to f inverse. What is the relation between 2, 3 and 3, 2? They are nothing but mirror images of each other against the line y equals x. That is what is the relation exercised by the points x, y and y, x. That means x, y and y, x if plotted in the Cartesian plane are nothing but the mirror images of each other corresponding to the line y equals x acting as the mirror. And therefore, if this is true for one point falling in f and f inverse, it is true for every point of f and f inverse. That means inside f inverse are points which are mirror images of the points of f. And that means the entire graph of f inverse is obtained by taking the mirror image of the graph of f against the line y equals x. That is why the graph of f inverse from the graph of an invertible function f is obtained by taking the mirror image of the graph of f against the line y equals x acting as the mirror. That is what is the rule. And thus, once we have understood that how in the world, if we have the graph of an invertible function, how can we very successfully come with a graph of f inverse? Once we have understood this, that under which conditions, by what technique we can form the graph of f inverse from the graph of f, it's now time to apply this technique to the sine function. Because the sine function, as you can see, from minus pi by 2 to minus 1, 1 is a bijective and hence an invertible function. And so sine inverse definitely exists from minus 1, 1 to minus pi by 2. Once I am sure about the existence of sine inverse, how can I draw the graph of sine inverse from the graph of sine? So if I am sure that there exists sine inverse x from minus 1, 1 to minus pi by 2, such that we know sine inverse y equals x if and only if sine x equals y, then what do you think or how do you think can I obtain the graph of sine inverse from minus 1 to 1 to minus pi by 2 to pi by 2. What will be the graph? Well, let's go to the graph of sine and take its mirror image along the line y equals x. So, if I draw the line y equals x, this is how it will come over here with this blue line drawn y equals x. And if you take the mirror image of this, you are going to get this white graph as the mirror image of sine graph along the line y equals x, giving you the graph of sine inverse to be like this. This is what is the graph of sine inverse function, provided that the graph of sine function is like this. From minus pi by 2 to minus 1, 1. With this sine graph, I have successfully obtained this as my sine inverse graph. Once I successfully have obtained from the invertible sine graph with respect to minus pi by 2 as the domain and minus 1, 1 as the respective codomain, because this sine function is invertible over this domain and codomain, that is why sine is invertible over this domain to that codomain, and therefore I have guaranteed that inverse of sine function definitely exists, and therefore just by taking the mirror image of the graph of sine against the line y equals x, I have successfully drawn the graph of sine inverse, which is covering the domain minus 1, 1 and the codomain minus pi by 2, pi by 2. Now is the time for observation. Observe carefully. If I just talk about sine function over the domain minus pi by 2, pi by 2 and the codomain minus 1, 1, what is the behavior of the sine function? Let's start observing by considering points. Suppose I take this point corresponding to this point, this is the value of the sine function. Suppose this is x1, then this is y1. Suppose I go to the left of x1, that means I reduce the input, the output also gets reduced. This means what? If I increase my input, output gets increased. That means this is what is happening to the left of the real line sitting as the horizontal real line. And if I move here, taking something as the input, look at here, this is the output. If I increase my input, my output gets increased. This means what? As I am moving from minus pi by 2, pi by 2, increasing my points, the values corresponding to these points are also getting increased from minus 1 to 1. That is what is the behavior of the sine function. You increase the value of inputs, the value of outputs are getting increased, which means sine function from minus pi by 2 to pi by 2 to minus 1, 1 is an increasing function. That is what is the deduction which I have just now shown to you and concluded. I told you that if inverse of a function exists, both of them exercise the same monotonicity. That means if f is increasing, f inverse is also increasing. If f is decreasing, f inverse is also decreasing. So over here I just verified that sine function from this domain to this codomain is an increasing function. In fact, a strictly increasing function. There are no places in the graph where the graph is parallel to x-axis, giving you the information that at more than one point the value of the graph or the value of the function is the same. And that is why the graph of sine is a strictly increasing function. Let's see whether this rule of f and f inverse having the same monotonicity is verified in the case of sine or not. Let's look at sine inverse. function. If I take this as the input, this is my output. If I increase my input, just look over here, the output is getting increased. Similarly over here, if I see, take this as the input, get some output, keep on increasing the input, your output keeps on getting increased. And that means, yes, sine inverse also has the same monotonicity as the sine graph, and therefore sine inverse is also an increasing function. Let us write that as our observations about sine and sine inverse, which say that what do they say? That sine function from minus pi by 2 to minus 1, 1 is a strictly increasing function, which implies sine inverse x, because both sine and sine inverse will have the same monotonicity. This function from minus 1, 1 to minus pi by 2 is also going to be, or it is also strictly increasing function. But there was one more point to be noted. Yes, the monotonicities of f and f inverse are same, but what is different is their curvatures. If sine is concave upward, sine inverse will be concave downward. If sine x is concave downward, sine inverse will be concave upward, which is very true. If you look over here, yes, sine is increasing and sine inverse is also increasing. But first sine is concave upwards, then sine is concave downwards. But over here, first sine inverse is concave downwards, then it is concave upwards. That is what is actually being verified with sine and sine inverse here as well, which is true for general f and f inverse. The other point to be noted under observations comes out to be what? If you observe carefully, the information delivered by sine inverse is saying that whenever you put inputs from minus 1 to 0, the outputs will be delivered in this interval. That means corresponding to every input inside sine inverse coming from the interval minus 1 to 0, the sine inverse function is going to deliver the output inside the interval minus pi by 2 to 0. And if you plug in any input from the interval 0, 1 inside sine inverse, the sine inverse function is going to deliver the output in the interval 0, pi by 2. That is what is the observation with respect to sine inverse. That whenever your input is coming from this portion of the input set, then this implies sine inverse x is going to produce the output inside this particular portion of the output set. And if x belongs to this portion of the input set, then sine inverse corresponding to these inputs coming from this portion of the input set is going to produce output in this interval or this portion of the output set. That is what is something which is guaranteed about the behavior of sine inverse. Now that we are so aware about the behavior of sine inverse in contrast to the behavior of the sine function, let's plug in certain values and see how does the sine inverse function behave actually mathematically, symbolically in contrast to the sine function. So if I start with giving you certain points of the domain of the sine inverse function and then finding out what is the output produced by sine inverse, that is going to give you a good practice and visualization about the behavior of the sine inverse function. So let's begin that. Well, if I take, suppose for an example, I ask you to compute sine inverse half. First of all, you have to verify that half acting here as the input of sine inverse is actually a valid input or not. We all know that sine inverse can only take inputs from the interval -1, 1 and nowhere else. And because half is very much sitting inside the interval -1, 1, somewhere over here, because half is sitting in -1, 1, that is why half is a valid input inside sine inverse function. And because corresponding to every input from -1, 1, I have one and only one output from -π/2, π/2, therefore there will exist a unique output corresponding to sine inverse half. Suppose that output is, say, x. Just suppose that sine inverse half is x, which is that unique output belonging to the interval -π/2, π/2. But I have written over here sine inverse y is x if and only if sine x is y. So corresponding to 1/2, sine inverse is going to give you x inside this interval if and only if sine of this particular x is equal to 1/2. That means, what is it that we have to find? We have to find that unique x which is belonging to -half such that sine inverse half is x. That means we have to find that unique x belonging to -half over which when sine is applied, answer is half. That is, we need to find that angle in -half or -π/2, π/2, we need to find that angle, say x over here, which I am saying in -π/2, π/2, such that sine of that angle gives you half as the output. Because only when corresponding to an angle x in -π/2, π/2, you get sine x equal half, only then you can write sine inverse half equal to that same x. Now if I wish to find a certain x in this interval corresponding to which sine gives half, first of all you have to question whether this is a valid expression or not. Can sine give the output 1/2 anytime? Well, sine function has the range -1, 1. So yes, and because sine function from -π/2, π/2 to -1, 1 is onto, that means every member of the codomain has at least one preimage in the domain. And because 1/2 is very much a member of the codomain of sine, therefore corresponding to 1/2 in the codomain of sine, there will exist unique x in minus pi by 2, which will be the pre-image of this 1 by 2 under sine. So yes, there definitely exists some x in minus pi by 2 such that sine x is equal to half. What is that x? Look carefully. You also know very well from the basic trigonometric angles, you know that sine of 0 degrees is 0. You know that sine of 30 degrees is 1 by 2. Sine of 45 degrees is 1 by root 2 and so on. Now you can see that sine at a certain angle is giving you 1 by 2. That angle is 30 degrees, or in radians I can say pi by 6. So because sine of pi by 6 is coming out to be 1 by 2, can I straight away write that x is equal to pi by 6? No, you have to verify first whether this x is actually lying in minus pi by 2 or not. Because my task was to find that x belonging in minus pi by 2 at which the sine is giving the value half. And because pi by 6, which is 30 degrees, is definitely less than 90 degrees and greater than minus 90, that is why it belongs to minus pi by 2 such that sine of pi by 6 is equal to 1 by 2, which implies sine inverse of 1 by 2 is the unique value pi by 6. And this pi by 6 is belonging to 0, pi by 2 portion of the range of sine inverse, because I told you from the second observation that whenever your x will belong to 0, 1, sine inverse x will belong to 0, pi by 2. You can see from here, whenever you have x coming from 0, 1, and in this case you had half as the input, sine inverse is going to deliver values from 0 to pi by 2, and here it is delivering the value corresponding to half. The value it is delivering is pi by 6, which is very much between 0 to pi by 2. That is what is the behavior of sine and sine inverse functions, and like in this manner, you can pick up any valid input for sine inverse and see how you can obtain exactly unique value corresponding to every input, valid input for sine inverse, the output in minus pi by 2. I end my lecture over here. Next time I am going to tell you and take you to the journey of inverse of some other trigonometric functions, and we are going to deal with their properties. Thank you and take care.